All right, thank you all for joining us for today's webinar with Tektronix and Electro. Before we begin, I want to remind people who we are at Electro. At Electro, while we don't make the electronic testing equipment that engineers use, we do make it easier for organizations to procure and manage their test equipment. With an inventory of more than $1 billion and 11,000 product types, we carry test equipment from the top OEMs across the globe. Our global reach means that our inventory and our people are located where your people work. Electro provides end-to-end solutions for the complete test equipment lifecycle across many industries, including those you see on this screen. We are very lucky to have Shubha and Satish from Tektronix presenting today. They both have extensive industry experience with power measurements. Combined, they have more than 25 years of Tektronix experience. Shubha, I will hand over the presentation to you.
Well, thanks, Leon, for the introduction. It's always a pleasure to work with Electro. You've been a great host to us. So, as the topic says, we will be diving deep into power integrity, the challenges in mission critical and high density applications. We would like to talk about what is power integrity, what are the industry trends and the challenges associated with it. And a larger ecosystem, which is also called digital power management, and what measurements in terms of hardware, software, which Tektronix has to offer to you, with some of the demos, in which case we would be playing some of the pre-recorded videos with our live setup for different applications as part of the webinar. As Leon said, we would also be running a Q&A session. Feel free to jot down your questions as we run through the webinar. And this is, part of our webinar series. We started off with mastering power measurements in modern power systems in May of 2025, in which we spoke about, as you can see here, AC/DC SMPS related measurements. And in today's webinar, we will dig deep into DC-DC voltage regulators, PMIC and DPM. And in the next webinar, we would like to broadly cover the power delivery network and its associated things. This is the larger integrated power system. There are many things happening, and we would like to focus to certain applications like automotive, traditional power systems, and the growing things like energy storage and aerospace and the challenges that come along with it. So I think power integrity, it's a industry-wide used term. So we as engineers deal with it almost, when whoever was working on power, VRMs, PMICs. So power integrity is something that one of us would have come in one or the other phase of our, the work. There are many definitions that are available on the website, which kind of says that power integrity ensures that there is a clean and stable power which needs to be delivered to different components of the circuit. And also the quality of this power from generation to consumption needs to be pretty clear. And not just that, so the power that comes should be acceptable within the tolerance limits. So as you can see, the example, that image that is shown here, the power that has come from a battery, which is like 42 volts, is getting converted to 5 volts. And there are different modules in my test system which requires different power levels, like a buck converter, boost converter. So there are different memory modules, LDOs. So they're not operating at the same voltage or current. So they're operating at different power levels. So basically power integrity should ensure that the power which is going to these different components in my VRM is stable, it's of a very good quality, and it is within the tolerance limits. I would like to reiterate the quote from Steve Sandler, who is perceived as an industry expert in power integrity and is also an MD of Picotest, who says that with the surge in high power computing and new PDM topologies evolving, power integrity and PDM validation are kind of essential, and the measurement-based modeling kind of guarantee and gives confidence to the designers to make sure that their system is working as per the intended performance. So we closely work with industry experts to design the measurements that is offered on our oscilloscopes, which we'll be talking in the coming slides. Uh, I just give a fundamentals of power integrity, but if we have to relate like where does it fit in my workflow, I would like to run a typical workflow of a power integrity design. So you might fall in one or more of this, but this is generally an industry-wide used workflow. It can change depending on the application, but more or less would kind of focus on some of these terms. Like it starts with simulation tools, and then it is followed with VRM components, validation, which includes number of blocks like efficiency. Like these are some of the measurements that we deal with as we operate with some of these components like control loop response, and then come some of them like platform validation, which includes time sequencing, overshoot, undershoot, and some kind of like PDN testing. And the last stage would be high-speed debug, where includes jitter, noise measurements. So what we have seen from our experiences as designers, we face power integrity problems at each of these stages. In most cases, some of these problems will be found like towards the end of the design cycle, where it becomes really hard to rectify that. But if I were to using a right tools, so one can make sure that the issues are found at an earlier stage, so that the cost of correcting that as we move towards the end of the workflow would be minimal. And we kind of provide tools to rectify those issues, measure them, and make changes to my hardware circuit well ahead of it getting into the final stages. So power integrity and the workflow, so where does it all fit in? And it's an industry-wide term which is called digital power management, be it either in the server or in the rack system. So there are different blocks that get into it. Like in most of the modern systems, especially with AI and high performance computing, so we are dealing with multiple power rails, and there is dynamic voltage scaling. There has to be a tight tolerance, and some of the components like CPUs, GPUs, FPGAs, and some of these high-speed signals, they require efficient and stable power delivery. In fact, the image here, it kind of illustrates a typical DC power flow. So like the supply coming from, getting into server racks. So here we can see that, managing power across different loads is really critical. In fact, power integrity is challenged by high frequency noise, dynamic core currents, and coupling from clock data lanes. So here I can say that power integrity in this ecosystem is also kind of affected by signal integrity, which will essentially lead to crosstalk and jitter, which will be something very interesting in our next webinar. But I would like to, kind of say that some of these things really form part of the ecosystem. There is a shift in how the industry is adopting to latest trends. Like in mission critical and high density environments, power delivery needs to ensure there is precise and reliable power that is getting delivered to different components. And some of those systems can be like aerospace, automotive, or AI data center, which operate under tight constraints. And there can't be any issues with instability and inefficiency. A small error can become a huge one, so there is really no room for making errors. So with these, you can see some of the trends on the left, like high power density, increased efficiency, and some of the transient loads, multiple output topologies, and the shift from silicon to silicon carbide and gallium nitride, which is demanding more or a higher switching speeds and higher voltages. And with these trends, there are challenges that is being added onto our workflows, like accuracy, which is non-negotiable for mission critical, and some of the safety and probing becomes really important. So I need to measure very precisely and in a really compact form factor environment. And EMI EMC is also something that's really hard to measure. So as engineers, we must evolve our validation strategies in order to meet these demands without compromising on the reliability. So it may sound like too many things coming into my workflow, or I'm overwhelmed by which should address. But I think as designers, you don't need to worry because we do have right tools from Tektronix. I can confidently say that 90% of the problems that is coming with the trends are addressed by the tools like hardware and software that we offer in this webinar. So like in the coming slides, I'll show some of the measurements for sequencing and transients, ripple analysis as part of digital power management, and few other things will be also discussed. So, but I could say that there are good set of tools available in the industry, and Tektronix is in forefront to address some of the new challenges that is introduced as the trends evolve. Let's see, before getting into the measurements like transient ripple, what are the signals that we are thinking about? Yes, there are measurements, there are tools, but what are they trying to measure? How do they look? You might have come across one or more of this. Like if you have a switching device, there is a switching ripple, which kind of looks something like this, like you're measuring continuously and there's a ripple when the device is switching. That could also be some of the example of the power rail signal that is coming in. Like if you could see the first diagram which I show, you have a buck converter and you have different modules, and the power needs to be delivered to different components through the power rails, and what that voltage or the signal that could be a switching ripple. It could be noise, sometimes high frequency external noise, which can coming from a Wi-Fi source or another system that is sitting there, could introduce that noise. And these noise or the ripples can be analyzed using spectrum view that is available on the scope, and there are tools like eye diagram, time interval errors, which can help to measure these noises. And at least from our experience, we have seen that these events like ripple or high frequency noise can be happening at the same time on a single PDN board. So how to measure them, characterize them is a tricky part, but that has been simplified with the tools that we will talk about. I think if you remember in the previous webinar, so we discussed one of the software application like the power, and in this I'm going to talk about the digital power management. So this is like an automated license-based software that is built onto Tektronix MSO5 and 6 series oscilloscope. We have characterized different measurements like ripple, transient, power sequence, jitter, and PSIJ based on the test points, the different blocks within the PMIC circuit that you're dealing with. And there are different algorithms that is written and kind of automated using the scope autoset feature, where you don't have to worry about the vertical and horizontal scales. That is ready for you, which we'll see in our demonstrations that is being played. And as these the designs become complex, so it is not limited to just one rail or one type of switching ripple or one type of noise. So there can be multiple such things coming in, so you're not limited by the number of channels that you have on scope. So you might have a MSO5 with 4 channels, but if you really want to go up to 8 rails or even beyond that, you can stack multiple scopes and synchronize them, which can be made seamlessly with the PC software. Here you can have many scopes, and you can connect them through LAN or an USB, and you can do more than the rails that you can do it with one oscilloscope. But with stacking them, we have cases where we have even gone up to 16 rails without much delay. So ripple, I think it's something that we have studied in our academics, so which is basically the AC voltage that is superimposed on my DC output of a power supply. So measuring this ripple on a just using a time domain, it's not so easy. So because there is low frequency, high frequency component, and with Tektronix tools, we have spectrum view feature where you can visualize that on a frequency domain, see how the ripple is there, and you can configure at different frequencies. Like you see, you can set a ripple frequency per rail and compute it for the full cycle, or the complete acquisition, or cycle by cycle. So these are some of the debug tools that is available, which will help you get details into what the signal is and make sure you don't miss out any of the transitions or during the switching. A ripple on ripple is something that is more simplified with the DPM app and the power rail probe, which we are going to see next. So I think one thing that designers face challenge is you are doing power conversion, you are making sure that the power is delivered to different components, but timing is really critical here because you are dealing with pretty much like nanosecond and picoseconds of time. So you have to make sure that the device settles soon and there is not much delay. So how much time it takes for it to turn on and turn off is something that one can do it. Like you give an input and output, so what is the delay and how fast my device settles. So there are measurements to help you do that. And there are some of the basic amplitude measurements, like where you can measure overshoot, undershoot, how much was the overshoot, undershoot during my turn on and turn off period, and what is my DC rail voltage. And there is also a automated report generation. As I said, these are the automation tools that is added onto the scope. You could generate the report either in a MHD or a PDF file. So basically, you can run tens of experiments, save the data in a PDF file, which can be later used, as documentation or for future reference. So along with report, you can also save that as a session file, which you can later recall with the waveform saved, or as a setup file if you're to hand over your work to someone in your team and you don't want to lose your work. So you can just save that and let that be stored in a repository from which the other person can continue. So all these features are built onto the Tektronix scopes with software capabilities added onto it to provide a complete measurement solution for you. With that, I will just hand over to my colleague, Satish, to talk about some of the test systems.
Let me just take some time to talk about the test systems, the recommended test systems. My colleague Shubha gave a brief overview of application use cases and different scenarios. So now let us look at the standard test systems which are actually being used to make measurements. Generally the most commonly used ones are the scopes. So I'm just showing here MSO 4, 5, 6 series scopes, which are our flagship scopes in this domain to do the power rail analysis. It can do much more. So that's an example, but there are many, any kind of scope can be used in that aspect. So, so talking about probes, so there will be many varieties of probes, starting from voltage probe to current probes. And also the isolated probes are one of the key probes nowadays if you're actually looking at some isolated measurements. So we will talk about that as well in the future slides. And along with probes and scopes combo, so we will use along other instruments like power supplies if you are actually trying to mimic some of the power rails outputs. You can use standard very high quality power supplies like the ones from Electro automatic, and so there'll be power supplies from Keithley, DMMs, and there'll be AFGs to generate if you're actually testing some of the control loop on these power rails systems. So we will use an AFGs to generate the required pulses. So that's another group of instruments. And along with all that, so we would definitely need software solutions, which software applications which are tailored to do some of these important measurements, which we will be talking about in the future slides. And Shubha also spoke about many of the measurements in our slides just now. So so when you talk about scopes, main thing to remember is that we should actually have the lowest noise from the measuring instruments. So that's why it's very important to make sure you get the right scope for your test setup. And the accuracy of the measurements is something which is very important. And sometimes you might want to analyze many rails combined together. So so generally, like earlier scopes used to be like maximum of 4 channels. Now generally the scopes come with 8 channels by default, and it's you should choose how many channels you want on the scope to analyze those many number of rails at the same time. And also you need to make sure you have the memory depth of the scope, like the record length of the acquisition should be high enough. If you are looking at debugging some of the complex signals, so you need to look at a lot of data, and having a sufficient memory depth is also important. And talking about probes, so the important things about probes is like you should have a probe which has the highest IDC offset. Let's say if you're measuring some of the rails which are as high as like generally automotive rails are like 48 volts, or like it can be up to 60 volts. So you should have the right probe to capture those signals and make the measurements. So not all the probes can have that DC offset, so you should keep in mind about that. And you should also keep in mind about the dynamic range of the probe in order to accurately capture the signal. And you should know the probe loading, which can actually impact the signal what you're capturing. So make sure you have highest loading at a DC, and if you're measuring, you should have a lowest loading to accurately see the AC components on the power rails. And so talking about softwares, so softwares are important to reduce human manual work, so you can eliminate a lot of manual processes with the softwares. So softwares are intelligent enough to look at your rails and say what is the voltage at which it is running, and it can actually do a lot of steps automated for you. So we will look at some of the examples actually how a software can help you to speed up your process of testing. How to probe a probe for power integrity testing? So there are various types of probing, starting from a simple coaxial connections. That's like a very easy connection with which is very low cost way of kind of probing to measure the signal. But yeah, the thing is, it is a 50 ohm termination one, and it will actually not have any ground loops. It can also have a best bandwidth. But the problem with this one is like you can actually have a limited offset range, so you cannot look at very high offset signals. So if it's a very small voltage DC offset, then actually this is a good best way to measure your power rates. And other ways are like you can load it with an 1 mega ohm of coupling. So our differential probes are like high voltage probes. Definitely the unknown passive probes come with default of that 1 mega ohm of termination. And so that's good if you're actually looking at lower loading. So if you don't want to load your setup, then this is the best way. But the problem with this one is like you cannot have a higher bandwidth. So then generally the bandwidth will be less than a gigahertz. And if it's a 1:1, then it will be lowest noise. But if it is a higher attenuation, like 10:1 or like 100:1, so then the noise in the system will be amplified with that factor. So you should be mindful of that. And it can actually have, there will be some high frequency components which can be reflections, and you should be careful that can come onto your measurement and may give you some wrong results if you are actually looking with 1 mega ohm of termination. So then the next termination is like a 50 ohm termination, which is again the most common one. So as I said for coaxial one, so this is again you can go with I mean, if you go with, you can go with an 50 ohm termination, provided that you are not loading your system, but it will actually have a higher bandwidth. You can go more than 1 gigahertz of bandwidth, and it will be the bandwidth of the scope, which will be ultimately coming into picture here. And also it can lead to issues if you're actually if you're I mean, the impedance of your PDN is less than like less than a ohm or like very small, then the 50 ohm load can have significant loading issues and can dissipate a lot of can lead to a lot of losses in the signal. So you should be careful of that. And I think having said all the different types of probing, so the one of the most common or like the most best ways to probe in this kind of analysis is with an power rail probe. This is a specialized probe which we have from Tektronix, and also other vendors also provide this. But the main thing about this probe is actually like you can actually measure a common mode voltage or like the DC offset up to 60 volts. So this is one of the key feature of this, and this comes with a 50 ohm termination, and because of which it will not have any reflections, and you can actually have the best measurement, and you will have one volt peak to peak of AC signal, which can be measured on an up to 60 volts of DC. So this is one of the most useful probe when you're actually looking at power rails. So let's see some examples also in the coming slides why this probe makes a lot of difference when you're measuring your power rails. So since I spoke about the various probing methods, so there are different probes other than power rail. So in the first column, so I'm talking about power rail probe, which has the different features, and we also can go with other probes like high voltage differential probe or standard differential probes or a passive probe. So each one has its own advantages and disadvantages. So you have to choose depending on what's the type of loading you want on the signal, and what's the voltage you are going to measure, and what's the common mode voltage you will have in your power rails. And I think all of that combined, I think it's a trade-off which you ultimately will be you will keep in mind when you're measuring, when you're selecting the which probe you want to use for your power rail measurements. So similarly for voltage probes, so there are various current probes as well. I have a list of current probes. The very first column is a newly introduced current probe called TICP, which is a shunt-based current measurement. I'm just trying to compare various types of probes along with the advantages and the disadvantages of each probing. So depending on like if you are looking at a band, for you, if bandwidth is important, so then I think all the probes except the SMUs and DMMs are the best ones. But for you, if it's like if you are looking for isolation when you're doing the measurement, so a Tektronix isolated current shunt probe, and also a TCP series current probe can be used. And if you actually look, there are various deciding factors actually, so you can refer this table and see which is the right probe for you to use for your measurements. So I'll not go in detail, but this is a good standard selection guide, I think, which you can actually refer. So talking about the differences actually, like why do I need a power rail probe, specialized probe to measure a power rail? So in this example, I'm actually quickly showing in 3.3 volts ripple of my demo board, and I'm trying to measure the same signal with a passive probe, and on the right side I'm measuring the same with an power rail probe, and you can clearly see the difference on how a passive probe can see the signal compared to a power rail probe. And that that's in default comes with attenuation things which actually are inbuilt in the passive probe, and it will amplify the noise, and so you will not have it can, if you're actually not terminating with 50 ohm termination, it will have reflections, and it can also cause a lot of ground loop issues. So that's where you should be very careful when you're actually measuring the power rails, because you want to make the measurements like the ripple. So that's, you need to measure that very accurately. So that's why a power rail probe solves all these problems, and you can actually have the best measurement possible. Similarly for old current, I'm just showing in current probe, like in isolated current probe called TICP 100, which actually we are trying to measure a current from coming through a small microcontroller. So it has different stages like sleep stage, wake up stage, and then it has a lot of communications which is actually happening between the peripherals. And you can see the current flowing in each stage. And the same current measured with the power rail probe, the isolated current shunt probe compared to an standard TCP series current probe. So there's a lot of difference. And you will have to be you have to be mindful of which probe you're actually using to doing the measurement, because you need to measure that accurately. So, and also you will be looking at some of the very transients, like when the microcontroller has a different transitions. Also in this case, if I'm looking at very low currents like microamperes or like milliampere of current, so then a current shunt probe with a 50 ohm termination can actually see that very accurately compared to other probes in the industry. And TICP is such a probe which can actually show you these currents very accurately. So in this screenshot, I'm just showing different stages of the microcontroller transitions, and I can clearly see that more accurately within TICP probe. With that, actually, I have a few demos. I'll just quickly show one of the demo videos where I'll be showing a demo of a multi-rail power analysis with an Tektronix solution, and also I'll be showing another example of high power application like mission critical applications. If you're trying to measure the power rails in a mission critical applications, so how do you do that?
Hi, I'll quickly show the demo of power rail analysis using our power rail probes. I have a demo board here, and I also have two power rail probes connected. So basically, power rail probes are used to do analysis of various power rails, which can actually have various bandwidths. Like we have 1 gigahertz model and 4 gigahertz models, and that can be used for various applications which have an offset voltage starting from like a few millivolts to up to 60 volts. So that's depending on which application you are using this probe, and you can just set that offset and do the power analysis.
Demo, I have a Beagle demo board, which is a demo board with the microcontroller and various peripheral units in it, and it has various power rails. Basically, I'm trying to analyze the power rails actually of this board. It's a very few volts power rails, and I'm trying to look at the ripple and various statistics of the rails. To do that, I have our digital power management software. It's called DPM, so which has various measurements for power rails. So we have ripple analysis, we have transient analysis to look at various transients. Then we have power sequence analysis to measure the sequencing, like turn on, turn off times. So we can do the jitter measurements of the power rails and also the high speed serial lines. And also we can also look at how the power supply rails can affect the jitter on the high speed serial. So let me add in the ripple measurement, which is the most common measurement which is done on the power rails. So as I add the measurement, I can just go to measure and do power rail auto set, which will actually set my automatically find out how much is the offset voltage of the power rail. So you can actually see that it is measured around 1.12 volts of offset, and which is already compensated for that, and enter that in the offset settings here. So by default, it has actually set limiting my bandwidth up to 20 megahertz. I can actually increase up to 250 megahertz if you want to look at more ripple components. So I would need some more record lengths. I'm just trying to increase some record length on the screen to see more data. And I'll double click on the measurement, and actually I can look at the spectrum component of the ripple. So I'll do a spectrum view auto set, which will actually add the spectrum for the power rail and show me the prominent components of the ripple. And you can see there is a markers, and every acquisition it actually has different markers. So in this acquisition, you can see that the prominent component of ripple is around 1.07 megahertz. I'm just going to see how much is a ripple at 1.07 megahertz. So I'm just going to go here and enter 1.07 megahertz, and you can see that I'm measuring around 22.8 microvolts of ripple of RMS, and also around 43.90 millivolts of peak-to-peak ripple at that frequency. So I can do that at various frequencies. So yeah, so that's one of the most common experiments we will do. So now I will also show you how do I analyze multiple rails. So in this case, I am connecting two rails. So I'll add a measurement. I'll remove this measurement. I'll add a new measurement. Go here, DPM, and I'll just select two rails. And I want to just do the ripple measurement on two rails. I'll just add that, and I'll just do run stop. So as I add that, I just need to go here and select the channels which is connected. So channel 1 and channel 2. So are the rails, and as I do power rail auto set, it will actually do the auto set for both the power rails which are connected and show me the prominent frequencies of ripple. Okay, so now we have seen the demo of an multi-rail power analysis using power rail probes. Now let us look at another use case of high power application, which is used for mission critical applications like aerospace and defense. So I have a demo board here from Corvo, and it has various stages here. So it's a 3-stage demo board which is used to generate RF pulse, RF power amplifier voltages and currents, and which is actually creates the pulses with the different stages. The first stage converts from 320 volts to 48 volts step down converter, and the second stage, 320 volts to 120 volts, and the second stage from 120 volts to 48 volts, which can be tuned. So it can be tuned from 20 volts to 65 volts, and the third stage is the power amplifier stage, which actually creates the pulses required for RF applications. So what I'm doing here is I'm trying to monitor the voltages on the second stage, the power rail output from the second stage. I'm actually using both probes, like passive probe and then power rail probe. I want to show you the differences between how we capture the signals with both the probes. And I'm also trying to capture the switching node output as well, just to show some of the transients which are happening. So as you see in the screen, so the channel 5, channel 4 and channel 5. So channel 4 is the power rail probe output, and the channel 5 is the passive probe, which is actually captured in the oscilloscope. So, and you can see that both the signals look similar. So, and I'm actually capturing an 48 volt power rail here. So I'm just configuring that offset in the scope. So, and for the channel 5, so it's a passive probe. So I cannot see that 48 volts, so offset. So, and that's why I'm actually capturing the signal in the AC coupling mode. I'm only seeing the AC component. So with this, so both of them are looking similar. And the main reason is actually I'm limiting the bandwidth up to 20 megahertz only. And with that, I'm seeing an switching ripple here. So that ripple is mainly due to the bad tuning. I'm actually using a higher resistor at the output of the higher impedance at the output section. So that's the reason you're seeing more ringing, more ripple on the band at the loop bandwidth. So so you can actually simply measure the ripple, and it's around 16 millivolts of RMS and around 50 millivolts of peak to peak. So this looks pretty similar between power rail probe and passive probe. So now what I'll do is actually I'll just increase the bandwidth to 250 megahertz in both the cases. And here actually you can see a clear difference between. So here you can see the clear difference between power rail probe and the passive probe. So the power rail probe can actually see the switching node noise. So there's a switching noise actually which is coming up in the power rail output. So which actually can be seen in the power rail probe only, whereas the passive probe is actually completely missing that. I can actually show you that by adding in the switch node output as well. So this is the switch node output. I'm just trying to overlap that with the other signals, and you can clearly see that at the switch node output transitions. So you can see that's switching ripple, switching noise. Whereas that can be seen on the power rail probe only, whereas the passive probe cannot see that. One more thing to remember is to note is actually you can see that there's a much higher noise on passive probe compared to the power rail probe, which is very important to see, because if you're going with higher bandwidth, then power rail probe sees very less noise, very stable output compared to the passive probe, and you can make much accurate measurements with the power rail probe. Thank you.
Okay, that was a demo of power rail probe under different applications. So you can, I think you're able to appreciate the amount of detail the power rail probe provides compared to any other traditional probing. So that's one of the important critical need for today's applications. So with that, so I will quickly go to the summary. I think we discussed about various applications and demand, growing needs for higher density and faster switching applications which require a greater efficiency. And I think that's one of the today's trend. I think most of the people working in power electronics are working for that. And as switching speeds increase, so there'll be more ripple and there'll be transients, and so you need to make the sequencing of different power rails very accurately, and there'll be jitter, and also there'll be compliance issues. So measuring them and making sure that you have the right, you have the best design. So it's very important. So to do, there are a lot of power rails. So to do test all the power rails manually is a tedious job. I think it's a lot of work. So automated measurements are the key actually. So as I showed, some of the demos, how can you actually quickly add a measurement, do a lot of, auto set and add a spectrum plots and look at a lot of big things. A lot of things are automated in the measurement software, so I can actually make use of that, and using the software features is important to reduce the human effort. And last but not the least, I think the proper probing, you should actually have the right probing to minimize the ground loops, and also you have to enhance the common mode rejection ratio to accurately measure the signal. So some of these techniques which actually we just discussed are very important. You should use the right probing technique to see the accurate signal. So with that, so I think that we have a lot of tools for you to refer here. So we have different application nodes. We have a data sheet actually which talks about the digital power management solution, and you can get to know different use cases of that. And we also have an interesting ebook from Corvo, so where you can actually learn from power management if you want to learn from the scratch. So you can get to know some of the basic stuff there, which is very useful if you're actually learning some of the key important design for power management ICs. Yeah, so you can refer those resources. So with that, I think we are just coming to the end of this webinar here. So we had completed 2 webinars by now. So this is our second webinar. So in the first webinar, we discussed about how do we design an SNPA circuit, and what are the key factors to take care, and what are the measurement challenges there. So mainly we discussed about that in the first webinar, and in this webinar actually we spoke about how do we characterize a DC-DC regulator, voltage regulators, and what are the challenges there, and what are the key measurements which will be looking at there. So that's for this today's webinar. And in the next webinar, so we will actually talk about the system as a whole. We will look at how a power distribution network is designed, and how do we make a stable regulator and a stable design. So for that, doing that, so we need to measure a couple of things, like we need to make PSIJ, we need to measure the crosstalks, so we need to make the control loop response, we need to measure the power supply rejection ratios, also we need to measure the impedance, the PDN impedance. So there are a lot of interesting things we will be doing in that stage as well. So that's coming up right in just a couple of months. Stay tuned for that. And yeah, as an action item, so I would request, if you are looking for any live demos, please reach out to one of your local Tektronix representative and ask for any tailored support, or like if you have any need of any hardware or evaluation tools, so you can connect to us. So you have our email IDs here, and yeah, we can work towards to solve the next generation power integrity problems. With that, I'll hand it over back to you, Leon.
Thank you, Satish. We engage with both Electro and Tektronix on LinkedIn. We encourage you to follow our company pages to stay in touch. So some of these frequently asked questions that Tektronix application engineers get asked. Question one, maybe I'll address this to you, Satish. In our multi-rail validation workflows, setup consistency is a challenge, especially across shift and teams. What automation features do your scope-based solutions offer to improve repeatability and reduce manual rework?
Sure. Yeah, I think this is one of the most common use case. There'll be a lot of people using these the scope, and they'll be using the setup, and having the repeatable thing is something which is important. So for that, actually, we have some of the features in the scopes, like you can save the sessions, whatever you worked on, and you can recall it later, and we can actually easily reproduce some of the test systems, like we have some of the features like power rail AutoSet, like spectrum AutoSet. With that, actually, you can navigate to the frequencies at which the problem is occurring, and you can isolate them very easily. And we do have a lot of support, especially with respect to PI commands. So we do provide programmatic interface if you are automating the test setup and making any automation around it. So I think, yeah, we are trying to make the life easier day by day for the users, actually. So please let us know if you think any more support is you require from in your setup to make your life easier.
All right, great. Thank you, Satish. Let's look at another frequently asked question here. Maybe Shubha, if you're still with us, I'll address this to you. So the question is, we're seeing some instability under load conditions, and I suspect ripple on ripple might be a factor. How do your power rail probes help surface those details compared to standard passive probes?
Thanks, Leah. That's an interesting question, and something which we get asked like every time our application engineer goes to the customer to do some demonstrations. One thing that comes straight away is, how do I probe? How do I connect this probe point to my board? And why should I even consider specialized probes like power rail? As Satish illustrated in one of these slides, more often we try to go to the traditional passive probes or the coax probes, but there is also a trade-off with the cost that we do, but post measuring the signals. So we've seen that, especially for mission critical applications, if there is edge that's missed out, if there is a small noise during the transition that's missed out, can affect the designs really bad, as you saw in the workflow as you move towards the right. So it's hard to fix those issues. So picking on the right probe, power rail probe in this case, is really important to make sure my device is operating and I don't compromise with the quality. And also, I think you saw in one of the demos that we showed, like there's a transition, and when it is measured with the passive probe, you just see it's a plain sine wave. But power rail probe is something that picks that transition when it is a falling edge or a rising edge. You see a dip, or you see some variations happening in the signal, so which is not seen in passive or the coax probes. So I would say that applications like these, power rail probes are something that we should be investing. It comes with different bandwidth options, 1 gig, 4 gig. So based on your needs, I think we should be opting for more precise probes because these are critical applications.
Thanks, Shubha. Satish, maybe you can help us with this one. I've seen noise artifacts that turned out to be probe related. Can you explain when it really makes a difference to use specialized probes like the ones you showed and when standard probes are good enough?
Yeah, sure. I think some of the things Shubha explained matter here also. So I think in my slide, actually, I showed a comparison table of the impedance, the scope, the probe offers. So let's say if you're actually trying to measure very low ripple, so then having that 50 ohm impedance is important because you don't want to have any reflections. And so if you're actually trying to measure with an higher offset, so depending on how much offset you need, let's say if you're not looking for very high offset, so then I would say just use coax cable and get done with it, because that's the best way. But actually, if you're looking for more than like 3-4 volts of offset, then I think different probes like differential probes are if you're looking for like very accurate measurements and very high offsets. So I think our specialized probes like PPR probes, power rail probes are the ones which make a lot of difference. And it all boils down to the what actually how much accuracy you're expecting and what is the end goal of your measurement. So that's where you decide on which probe you would need to use for your measurements.
Great, thank you, Satish. We are thankful you joined us today, and we just want to give a special thanks to Shubha and Satish with Tektronix for an excellent presentation. So on behalf of all of us, have a great day, everyone.